Okay, so in this video, we're going to look at two topics. We're going to talk about electropotential surfaces, and we're also going to talk about capacitors. But before we start with either one of those, let's just review just a little bit. To go back and talk about electric field lines. Remember, electric field lines are those imaginary lines we use to help visualize what the electric field might look like. We know that there's a couple of rules, but one of the important facts we know is they point out or away from positive charge, and we know that they point toward negative charges. Electric field lines point in the direction of force on a positive charge. So if I had a positive charge here and a negative charge here, the electric field lines, I'm going to draw those in blue, would point from the positive toward the negative, and they'd kind of bow they always point towards, so we can draw some more, draw some real curvy ones. And on the same side over here, these will point away, point away. Okay. E, that electric field has the same direction. As the force on a positive charge. We know the magnitude of the electric field is found using the formula that it is the force per unit charge. It's the force divided by charge. We measure that with units of either newtons per coulomb, or we later learn sometimes we can measure that in volts per meter. Of particular interest, especially when we start talking about capacitors, is the idea of a uniform electric field. Uniform means that electric field is the same everywhere. Most uniform electric fields are made using two parallel plates. One of the plates will be positively charged. I should probably draw these on the opposite side sometimes, just to make it interesting. And one negative. Usually you can accomplish that just by connecting them to, say, a battery. If I put them up to a 12-volt battery, and I connect the negative terminal to one side and the positive terminal to the other. Usually when we do something like this, we let the negative terminal be at 0 volts potential, and the positive terminal then would be at 12 volts potential. We know there is a 12-volt potential difference between the two terminals. Let's suppose we have 12 volts. If the separation, let's let the separation between the two plates be 10 centimeters or 0.10 meters. If I separate them by that distance, I can determine the electric field by using the fact that the electric field for parallel plates is the voltage divided by the distance. So I get 12 volts divided by 0.10 meters, and I get 120 volts per meter. That gives me the magnitude. The direction, of course, we draw those electric field lines. In the middle here, it's going to be very uniform. I can draw uniform by trying to space them nice and equally. And it will point away from positive, and it will point toward the negative. Now, I'm not going to get close to the edges. I know it's not real uniform if I get close to the edges. But if I stay in the middle, it is. So if I really want to make this, what's the electric field? It's 120 volts per meter to the right. If we're not talking about a uniform electric field, if we're talking about a point charge, that electric field, we'll do a positive point charge. It points away from the positive point charge. It points in all directions. I can't draw three-dimensionally, but if I could, there would of course be lines, electric field lines, also pointing out of the screen as well. But I can only draw in 2 dimensions. And of course, they point away. And you can see this is not uniform because as you get farther away from the charge, the electric field gets weaker, lines get farther apart. The magnitude of the electric field here is just K, Q over R squared. You'll remember Coulomb's law says that the force is K, absolute value of Q, Q prime over R squared. But to get the electric field, we divide this by Q prime and we're just left with this. Okay. All of that was review because I want it to be fresh as we talk about equipotential surfaces. Equipotential means exactly like it looks like it means. Equipotential. Equal potential or equal voltage. An equipotential surface is a surface on which the potential is the same at every point. Conducting surface is always equipotential. That's an important fact. Let's think about this. If I had a piece of metal, I have a spherical conductor. we know that if I have a spherical conductor, that the electric field inside is going to be 0, and the electric field at the surface is going to be the same. All of these charges are going to distribute across the surface until they don't feel any force. If you can think of this coming out, there'd be more charges. Okay? So the charges will be at rest. If the charges are at rest, that means there cannot be any component of the electric field that's acting tangent to the surface. If there was an electric field acting tangent to the surface, then the charges would feel a force and they would move. But these charges all have a net force at 0. They've all reached a point of static equilibrium. So there can't be any component of the electric field that's acting along the surface. So we know that that is going to have an electric field of 0. If we think about what that electric field would look like, let's suppose we have this positively charged object, and I drew it kind of big. It is possible, however, that it would have an electric field. In fact, the electric field for a spherical object looks just like the electric field for a point charge, except that inside the sphere, the electric field is 0. But outside the sphere, the electric field lines point away. So we would have those same electric field lines just as if they were coming from the very center, even though they're not. Notice these electric field lines are all perpendicular to the conducting surface, and that is always true. Electric field lines are always perpendicular to a conductor, but that's because there can't be any component parallel or tangent to that surface. If there was, those charges would move until the electric field was, till the net force was 0. But just outside of the conductor, we can have an electric field. So that's what the electric field looks like. Equipotential lines for point charges, and I'm going to draw those in red, will look like this. They will look like concentric circles. I'm try to draw them equally spaced, but I may not do a very great job. That would be an equipotential surface. The potential at that point would be the same. Remember, the potential for a point charge, did we write that down? We did not write that down. The potential for a point charge is given by KQ over R. So if we choose a different distance, we get another equipotential surface. Now, these look like concentric circles, but truthfully, they should be concentric spheres. I just can't draw in 3D. So those are examples of equipotential surfaces, and you could draw as many as you like. If they're at the same distance r, then they're going to be at equal voltage. Now, if we want to think about an equipotential surface for a uniform electric field, here's our uniform electric field. We'll let this side be negative for a change. Negative, 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 negative. This side is going to be positive. So I want a little more room. I'm going to redraw this a little bit. Let's go horizontal. Let this be positively charged. come down here a little ways and draw a second plate. This plate is negatively charged. We'll connect them with a 12-volt battery. Here's the positive terminal. Here's the negative. Whoops. There's the negative. Okay. We would consider this to be 0 volts. We would consider this to be 12 volts. If I choose the point that's exactly in the middle, this would be 6 volts. That's going to be one of those red equipotential lines. That's an equipotential surface. Right there at 6 volts. There's another one halfway between 0 and 6 at 3 volts. And another one between 6 and 12 at 9 volts. Remember, I said you can kind of think of potential energy like height. So a positive charge that's way up here at 12 volts has more potential, and therefore more potential energy, than a positive charge that's here at 3 volts. They both have potential, and they both will want to move from the positive towards the negative. But the one that's at 3 volts just isn't going to have as far to go. If we draw our electric field lines, remember they point away from positive toward negative. And we can see another really important characteristic of equipotential surfaces and electric field lines. Equipotential surfaces are always, it's an important word in physics, perpendicular to electric field lines. It's really easy to see these are right angles. But if you look up here at the circular one, these are also right angles. Electric field lines are always perpendicular to conductors because conductors are equipotential surfaces, and they're always perpendicular to any equipotential. The field lines are going to be perpendicular. Knowing that, we can kind of sketch for some other surfaces. Suppose I have something like this. I have a positively charged surface, flat horizontal surface, it's vertical, positively charged. And over here somewhere I have a negative point charge. I know that when I draw electric field lines, they have to be perpendicular to the surface. So they're going to come out straight. They have to come out straight. They also come out straight here. So, and I don't know if I line that one up just, so that's going to be perpendicular right there. But you're going to also see they're going to curve so that when this meets, it's going to meet perpendicular. All of these should make right angles at the surface to the conductor. So they point away from positive, they point toward negative. We can draw some equipotential lines. This one's going to be fairly straight right here, fairly close. It'll make right angles with all of those. But by here you can see that that equipotential surface is going to be somewhat curved, so that all of these are also perpendicular. And then here will be somewhere in between. Okay, that tells you what an equipotential surface is. It is a surface at which every point has the same potential. What does that mean? Well, we know that the work done on a charge can be found using this. Let's go back up here and look at this uniform electric field. If I have a charge here and it moves along this equipotential surface to here, it didn't do any work. Why? Because there's no difference in voltage. The voltage at point A and point B is exactly the same. Absolutely no work would be done. If I have a charge and it went from here to here, and a negative charge would willingly go from here to here, then it's going to have some work. Let's suppose I had an electron. If I had one electron, that's a charge of negative E, and it went from 3 volts to 9 volts, that would be 6 electron volts of work that was done by the electric field on that electron. I didn't calculate it this time in joules. If I wanted to calculate it in joules, I would have said the charge was 1.6 times 10 to the negative 19, but it was really easy to do it in electron volts. Or if I have a proton, little positive proton right here, and it moved from here all the way to here, this is for the electron that went from A to B. Let's do a proton this time, and we'll call this point C and D. The work done on that proton would be Q. It went from C to D. Again, the charge on a proton is simply E. The voltage at C was 12. The voltage at D was 0. And that's going to be 12 electron volts. This was in volts. You can see why electron volts are so easy to use. If you want that to be in joules, just remember 1 electron volt is 1.60 times 10 to the negative 19 joules. So if I have 6 electron volts, I just have to multiply by 6. That's electron volts, that's joules per electron volt. That'd be 9.6 times 10 to the negative 19 joules. All right, I think that's all I want to say about equipotential surfaces. Let's move on to a really important concept, and that's the idea of capacitors. This brings us, I believe in your text, this is section 18.4. A capacitor is simply a device that's designed to store an electric charge. Used to be if you had a small camera, it's different now. you would have a flash and you'd have to charge your flash. And then once you took the picture, the flash would be used very quickly. That charge would flow and you'd have to recharge it. So capacitors can be charged, then discharged and recharged, but they store electric charge. And in doing so, they also store electric energy. Most capacitors are made up, well, pretty much all capacitors. They consist of two conductors with a vacuum or an insulator in the middle. Now we could make those of any shape, but by far the most popular design for a capacitor is two parallel plates. We've already been talking a lot about parallel plates. So you have one conductor. We're going to connect a lead to it. There's a piece of wire. Underneath it, you're going to have a second conductor. We'll have another lead on the other side. They're separated by a distance of D. One of the plates will be covered with contain a positive net charge, and the other plate will have an equal but opposite negative charge. Okay. Now, the reality is, if I have two parallel plates, I'll tell you what, I'm going to save that for just a minute. So that's what they look like. How do we define capacitance? The capacitance is the ratio of the amount of charge over the potential difference. We measure it with a unit called a farad. 1 farad is equal to 1 coulomb per volt. The more charge that it can store at a given voltage, the higher the capacitance. Okay. For a given design, the capacitance is a constant. Okay, so what characteristics determine the capacitance? Generally speaking, it depends on the area of the plates and how close the plates are together. So for a parallel plate capacitor, with a vacuum in the middle, we find that the capacitance is equal to epsilon naught A over D. A equals the area of the plates. So that's going to be in meters squared. D is equal to the plate separation. So that will be in meters. And finally, we have this constant. This constant shows up a lot in electromagnetic theory. It's called vacuum permeability. And it equals 8.854 times 10 to the negative 12 Coulomb squared per Newton meter squared. It's just a constant in physics. It's been found experimentally. So if we look at our formula, we see that if we want to increase capacitance, we want to be able to store more charge at a particular voltage, then we can either increase the area of the plates and make the area of the plates very large, or we can decrease the separation between the plates and make the plates very, very close together. In most capacitors, the plates are in fact very, very, very close together. And that creates a little bit of a problem. Most of the time, the way that problem is solved, instead of having a vacuum in between, they put another layer. If you think about a conductor, a piece of aluminum foil would be a good conductor. If I take another piece of, instead of aluminum foil, I take something like saran wrap or an insulator, a sheet of Mylar, Teflon, and put in between, and then get a second sheet of aluminum foil. That's the easiest way to make one. So you need a conductor, and then you need an insulator, then you need another conductor, and then usually what they do, they use very thin sheets of metal. They put a very thin sheet of insulator, is then they put another sheet of insulator, a second one, so it's layered. They have to have some leads attached to both of the conductors, but then they take the whole thing up and they roll it up like a jelly roll. If you can picture it, they just take all four sheets like that and they roll them up. The insulators keep the two conductors from coming in physical contact with each other, but they let that distance be really, really small. So if you ever open up a circuit and you see a capacitor, it usually looks like it's a fairly small little device. It usually looks round and it'll have a couple of leads coming out. You know that one of the leads will be connected. Let's just put a lead. There'll be one lead coming off the first conductor and another lead coming off the other. But when they wrap all this up, those two conducting plates are kept separate from one another by that insulating sheet. All right, if you want to maximize capacitance, you want a large area, you want a minimal separation distance. Let's look at an example. It says a parallel plate capacitor of 10 farads. So we got a capacitor of 10.0 farads. Has plates 1 millimeter apart. And the question is, what is the area of the plates? So our formula says, well, the capacitance is epsilon naught A over D. I can put it all over that. And I want to find A. So if I solve this for A, it's going to be C, D, or epsilon. The capacitance was 10 farads. The distance was 1 millimeter. I got to make that in meters, 0.001. And of course, epsilon, that's at 8.854 times 10 to the negative 12. I put all that in, and when I solve it, I get that the area is about 1.1 times 10 to the 8 square meters. That's huge. That's bigger than Manhattan Island. That's approximately 11,000 meters per side if this is a square. Well, all that to point out is they're in a 10 farad capacitor, at least not in everyday electronics. Capacitance is usually found on scales of microfarads or picofarads. Let's try and spell usually correctly. Usually in microfarads, which of course is 10 to the negative 6 farads, or picofarads. Pico is 10 to the negative 12. It's possible that you can also find it maybe in nanofarads, but they'll usually use either pico or micro. So let's change the problem. Instead of trying to have a capacitance of 10 farads, let's try to have a capacitance of 1 picofarad. So that's our capacitance. We'll let our plate separation still be 1 millimeter. Now let's find what the area is. Well, it's CD over epsilon. So 1.0 times 10 to the negative 12, 0.001 meter, and 8.854 times 10 to the negative 12. This time, the area comes out to be 1.1 times 10 to the negative 4 square meters. That means if we think of a square, that each side would be about 1.1 times 10 to the negative 2 meters, which is approximately 11 millimeters. Much easier to visualize a capacitor that's an 11 millimeters on each side, not one that's 11,000 millimeters on each side. All right, let's do just a little bit more just to get comfortable. We've got two basic formulas that we've learned so far. One is based on physical characteristics. In a vacuum, capacitance is epsilon naught area over the distance. In terms of its ability to store charge, capacitance is Q over V. So this example says the plates have an area of 2 square meters. They are separated by a distance of 5 millimeters, and it is connected to a voltage supply, so there's a potential difference of 10.0 kilovolts. You want to remember that that's going to be 10.0. Kilo is 10 to the third volts, so a 10,000 volt potential difference there. First thing we want to do is calculate the capacitance. That's very straightforward. So 8.854 times 10 to the negative 12 times the area divided by D. We're going to make that into meters, 0.005 meters. And that comes out to be 3.54 times 10 to the negative 9 farads. Negative 9 is nano, so 3.54 nanofarads for the capacitance. Second question says, okay, in that case, what is the charge on each plate? Remember, when you have a capacitor, both of the plates are charged. One of them will have positive Q and one of them will have negative Q. Okay, C is equal to Q over V. So Q is going to simply equal the capacitance times the voltage. So we have 3.54 times 10 to the negative 9 for the capacitance, and that's farads, and 10.0 times 10 to the third volts. That's at 10,000 volts. This comes out to be 3.54 times 10 to the negative 5 coulombs. We could leave it like that, or if we want to, we can change it. That's 35.4. If I make this 10 times bigger, then I have to make this 10 times smaller. That's how I always solve these. I know I like the exponents to be in multiples of 3 a lot of times. This is scientific notation. This is not scientific notation. The whole point in writing it like this is to recognize that would be 35.4 microcoulombs, because 10 to the negative 6 is micro. So either of these, this is the correct answer in scientific notation. There's nothing wrong with that answer. This is the correct answer if I just was asked to answer in terms of microcoulombs. There's one more question we can answer that we haven't yet, and that's what is the electric field between the plates? We know for a parallel plate capacitor, the electric field is simply the voltage divided by the distance. We have 10,000 volts. We have a distance of 0.005 meters. That comes out to be 2.0 times 10 to the 6th volts per meter. So a strong electric field exists inside of capacitors. It's very typical that you're going to get really large electric fields. Okay, so we're finished with the basic idea of equipotential services and sort of an introduction into capacitors. In the next video, we're going to talk about how capacitors behave when they're joined in series or how they behave when they're in parallel.